SwayamPrabha. Digital India. Educated India.
Let us begin with the lecture 44 of the course, in which we continue our discussion on Inviscid high temperature non-equilibrium flow. In this lecture, we would look at frozen, equilibrium and non-equilibrium flows. We would look at the characteristic time scales and length scale effects. We will look at how it works for normal and oblique shocks, and how curved and straight walls may affect the oblique shock shape. We pose a question here that in a high temperature internal or external aerodynamic flow, is it at a local thermodynamic and or chemical equilibrium or not, is what we would like to know. And additionally, if it does not happen like that, do substantially different conditions exist which are non-equilibrium in nature. So, if we try to answer this question, the answer is not very straightforward. We would just like to begin by saying that the flow would fit into one of the following conditions as follows. We begin with A, frozen flow. It is one where reaction rate constants are 0. So, the backward and forward rates are identically 0. The vibrational relaxation time tends to infinity, and therefore, when we are talking about fluid elements or particles undergoing such a flow, for example, internal flow through a nozzle or external flow past a hypersonic vehicle, they would not experience any chemical reactions, and the vibrational energy exchanges take infinite time, which means no vibrational energy exchanges take place. This is how a frozen flow would really react, and when we say it is a calorically perfect flow, then it is referring to a frozen flow model. On the other hand, if you look at equilibrium flow, it is one where the reaction rate constants tend to infinity, both the forward and backward rates tend to infinity. The vibrational relaxation time is identically 0. Therefore, when the fluid elements undergo this flow, they experience chemical reactions at an infinite rate, and hence equilibrium chemical composition is achieved at any location of the flow at any point of time. The vibrational energy exchanges also occur infinitely fast, and therefore, the vibrational equilibrium is also reached simultaneously. So, if we are noticing such a fluid particle or an element crossing a point x 1 y 1 at time t 1, locally at that point the pressure and temperature are given by P 1 and T 1, and it takes some time for the fluid particle to move to another location in the flow field, which is given by x 2 y 2, and it happens from time t 1 to time t 2 that it relocates itself, and then it finds itself in a different thermodynamic environment where the pressure and temperature are respectively P 2 and T 2. Now, as this locational change happens, the important question to ask is how quickly does the fluid particle adjust itself to the local changes of pressure and temperature as it moves from point to point of the flow field. So, if it is a case of frozen flow, no changes whatsoever would occur in the internal energy modes due to the collision between the particles, and the chemical composition of the fluid particle will be sustained. and that is precisely because of the 0 reaction rates and infinitely long vibrational relaxation times that we already discussed about. And therefore, essentially the fluid particle does not respond to or does not adjust at all with the changing local environment. In the case of equilibrium flow, it is the other extreme. All the internal energy mode changes or chemical composition changes which had to happen in response to the local pressure and temperature would keep happening from point to point, and that essentially means that the fluid particle adjusts instantly with the changing conditions. And again, this is possible for infinitely fast reaction rates and or 0 relaxation time. In reality though, these two extreme conditions, none of them really occur in an exact sense. Therefore, it may be that one of the situations is approximated or the other is approximated, and we can say that closely it is like frozen flow or an equilibrium flow, but not exactly so. While there may be situations where non-equilibrium can also be a dominating issue, and in that case we cannot consider the flow to be either frozen or equilibrium. We definitely have to consider it as a non-equilibrium flow, and this is a slide which we have seen earlier, but we are revisiting it because here there is a very important term that has been highlighted, the scale effect which comes up in a non-equilibrium phenomena, where the non-equilibrium flow could very much depend on the dimensions of the body. The size of the body becomes a very important issue in these kind of flows. Again, we remember that it boils down to saying that whether adequate number of molecular collisions really took place, so that the vibrational energy exchanges could take place during those collisions, or the chemical reactions were triggered during those collisions, makes a huge impact over here. And therefore, when the vehicle is traveling in low density high velocity conditions, or flow is happening through an internal passage under such conditions, then there is every chance that the non-equilibrium phenomena may end up dominating. The non-equilibrium effects are significantly enhanced for smaller bodies at higher altitudes. On the contrary, equilibrium flows, which we already studied in week 8 of the course, occur for larger bodies at lower altitudes. So, these are thumb rules which would be understood to a greater extent through more logical discussions why it really happens, but these thumb rules need to be remembered. Let us come to characteristic time scale and length scale effects in non-equilibrium flows. We define tau f as the characteristic time for a fluid particle to traverse the flow field of interest. So, we introduce a characteristic length scale capital L and a characteristic velocity, which could be a free stream velocity, for example, for an external flow, or it could be a changing velocity through a nozzle. Depending on the cross sectional area change of the nozzle, the velocity will change from point to point. So, you essentially have a length scale and a velocity to define the time scale here, tau f, associated with the flow. And there is another time scale which is important, which is associated with chemical reactions and vibrational energy changes, which is indicated by tau c. The c essentially comes from the fact that we are trying to bring in the effects of chemistry over here, and therefore, these two time scales are going to be very important for us. For frozen flows, it so happens that the flow time is much smaller compared to the chemistry time. That means, the time required for chemical reactions or vibrational energy exchanges to take place, and the flow time is way shorter, and therefore, none of those really happen. That means, the chemical reactions or vibrational energy exchanges do not find a scope to happen. While for equilibrium flow, it is exactly the other way around. The flow time is way larger than the chemistry time, so to say, and we have shown in these two figures for internal and external flows that how these length scales and velocities would matter for different situations where you have a very high speed flow. And the tau f is the residence time of the fluid particle in the flow field. This is the time it takes for the fluid element to flow through a nozzle or flow past the body that we just saw. It is basically the fluid dynamic time that we are talking about. Tau c is the time it takes for the energy exchanges within the internal energy modes and the chemical reactions. It is the chemistry time that we already mentioned. And we also talked about these situations. So, when tau f is way smaller than tau c, the fluid particle rapidly crosses the L length before any vibrational energy exchanges or reactions take place. In such a case, the flow can be assumed to be frozen, while if tau f is way larger than tau c, such exchanges or reactions have enough time to take place as the particle crosses the length L, and in such a case the flow can be assumed to be in local thermodynamic and chemical equilibrium. Non-equilibrium therefore falls in the corridor in between, which is essentially a very wide corridor, and that basically means the tau f and tau c become comparable, and in such cases the vibrational or chemical reactions, the vibrational exchanges and reactions occur at non-equilibrium, and therefore, we are talking about finite rate equations which would decide how far the energy exchanges and reactions would proceed as the fluid particle covers the length L. Now, when it comes to non-equilibrium normal shock wave flow, then we would need to look at it in the specific scenario of a normal shock. We consider a strong normal shock where the temperatures which are achieved are high enough to cause chemical reactions within the gas. The thin region where large gradients in temperature, pressure and velocity occur, and where the transport phenomena of viscosity and thermal conduction are important, is essentially what we call as the shock front. Now, we are going to discuss about these transport phenomena in much more detail when we visit them in week 10, where we discuss about chemically reacting viscous flows. For now, we are not going to get much into the detailing of these transport phenomena, but we are essentially going to talk about the non-equilibrium issues as they may occur in an inviscid case. When we deal with calorically perfect gas flow or equilibrium flow of a chemically reacting and or vibrationally excited gas, the flow in front of and behind the shock, they are considered to be in equilibrium. The only gradients in the flow properties exist almost discontinuously within a thin region of no more than a few mean free path thickness, which we call as a normal shock or normal shock wave front. So, in inviscid flows, we essentially talk about the Rankine-Hugonot conditions, where jump conditions essentially are imposed across a shock, and we try to see the upstream versus the downstream properties. In a non-equilibrium flow, all chemical reactions or energy excitations take place at a finite rate. Because the shock front is very thin, the fluid particles which pass through that front experience only a few collisions as they cross the front, and therefore, they do not have enough collisions to respond to that huge change which has occurred across the shock, and therefore, essentially the flow remains frozen. So, it undergoes a sharp change due to the jump conditions that we state them as Rankine-Hugonot conditions, and these jumps that we are talking about are imposed on the particles, but then they are not essentially responding completely to the change, because they have not undergone sufficient number of collisions to be considered to be perfectly in equilibrium. We say that they did not have enough time or enough collisions to respond to the situation, and therefore, this is kind of a frozen condition. We have a pictorial representation over here, in the sense that this is a normal shock, the straight line that we have over here, and there is a narrow region behind the shock which we have marked as A. We are measuring the x coordinate starting from the shock downstream towards the right, and this region A extends between 0 to x 1, let us say, where x 1 is a small dimension, and the flow behaves like a frozen one over this region. And then there is a much longer region B, which we consider to be a non-equilibrium region. It is of moderate length, and that extends from x 1 to x 2, and then comes another region which we are calling as the equilibrium one, which essentially extends from x 2 to infinity. And you have the upstream flow velocity u 1 and the downstream flow velocity u 2, which is essentially a function of x, and that is because of the non-equilibrium that is existing behind the shock. As the fluid particles move downstream of the shock, the finite rate reactions take place and the flow properties relax towards their equilibrium values. Simultaneously, the vibrational excitations are also going on. With this picture in mind, the shock wave now encompasses both the front and the non-equilibrium region that is behind. And if we are considering that there is a pure diatomic gas, let us say diatomic oxygen flowing past this shock, then in front of the shock wave, I mean upstream of the shock, you have a mass fraction of atomic oxygen equal to 0, while molecular oxygen mass fraction will be 1. And if you move downstream of the shock, immediately behind the shock, the atomic oxygen mass fraction would still remain 0 in the frozen region, but then it will start changing through the non-equilibrium region till it reaches an equilibrium value when it is into the region C. The properties immediately behind the shock front are obtained from the frozen flow results. So, you essentially use gamma equal to 1.4 in the normal shock equations for calorically perfect gas to obtain the properties in region A. And the CO immediately behind the shock front is still 0 because the flow is frozen, as we said. There is no reactions which have occurred, and therefore, the mass fraction of CO is 0 in region 2 to begin with. And then in the frozen region, which we are calling as region A, of course, we would have the normal shock relations for a calorically perfect gas. So, its continuity, momentum, energy, conservation, followed by two thermodynamic relations. One is the equation of state, the other is that for enthalpy, which essentially closes the system. These are the assumptions that we should recall. We have learned these in an earlier lecture. We have the continuum, steady, inviscid, no body forces, compressible and adiabatic assumptions coming up here, and it is essentially a 1D flow model that we are talking about over here. Further downstream of the shock, when it goes into the non-equilibrium flow, it is the region B. We have to talk about numerical solution of the non-equilibrium governing equations. We had discussed about the governing equations in the previous lecture. We are revisiting them here, and if you talk about a numerical solution, then we will have a very brief discussion in a later slide regarding this. We are talking about the species continuity equation that we learned there, and if you talk about the one dimensional steady model, then essentially it will be simplified further. The global continuity equation here, the momentum conservation equation, energy conservation equation, equation of state, and then additional equations for specific gas constant, molecular weight and enthalpy of the mixture. So, all this should be still fresh in your mind because we just studied it in the previous lecture. Depending on the shock strength downstream of the shock, the molecular oxygen completely dissociates or partially dissociates. If we are talking about very strong shocks, there may also be ionization, and therefore, there will be a gradual increase in the concentration of atomic oxygen. The mass fraction will gradually grow beyond 0. If you talk about a pictorial representation, this is how it changes from a 0 value for atomic oxygen mass fraction to an equilibrium value through a changing mass fraction region, which we are calling as the non-equilibrium region. So, the double arrow region basically shows the region over which the change really happens. The dotted or dashed line essentially shows the frozen level, and we understand that dissociation reaction is endothermic in nature, which we have learnt earlier, and the static temperature therefore would decrease and the density would increase. This is a very, very important fact which we have to keep in mind, and this has profound implications on the shock shape, which we will discuss later. Because of the dissociation, you find that the temperature which rose from T1 to a rather high value, which we indicate as the T frozen value, gradually reduces to an equilibrium value which is much lower. As it happened, as the gas cooled itself, it also gained in terms of density, and therefore, it went much beyond the frozen density value. Again, in density also there was a sharp jump across the shock, which we get from the Hugonot conditions. Ultimately, the flow properties would approach the equilibrium values downstream of the normal shock as it reaches the region C, and it can be computed based on the equilibrium conservation equations. We talked about the iterative technique in week 8, which has to be applied here. If you recall that we talked about trial values of this density ratio with which you can start the iterations and then stop within a few steps till it converges. We are not going to go much more in detail over here. Let us move on. Here is a brief discussion about the numerical calculation that you might attempt of the non-equilibrium region behind the shock. Remember, it is a one dimensional and steady situation that we are talking about. When it comes to the species continuity equation, under the one dimensional assumption, the equation would reduce to a form like this. Remember that the substantial derivative, in the substantial derivative, the time dependent term will go away. Further, because it is a one dimensional problem, it will the derivative will become an ordinary derivative in place of a partial derivative. Therefore, you write it now in this form. Similar changes or simplifications will happen in the other equations too. So, the global conservation continuity equation takes a form like this, a global momentum equation takes a simplified form like this, with some calculations shown over here for the elaboration sake. The energy equation reduces to a form like this, and once you are done with these simplifications, basically the numerical procedure will talk about the species continuity equation. The x distance is measured from the shock extending downstream. So, it involves the finite rate chemical reaction term W I dot, and the distance dx multiplies this term. This equation introduces the so called scale effect that we are talking about into the solution of the flow field, and it is purely because of the non-equilibrium phenomenon that we are talking about. Here we are just talking about a single molecular species dissociation. We took oxygen as an example. If it is a gas mixture, you have to write down a system of species continuity equations, including all the constituent gases in the mixture, and they have to be numerically solved. As a consequence of the above, all flow field properties would become a function of the distance or the length behind the shock, which we are demarcating as x. The above system of equations can be solved by using standard numerical technique for integrating ODs like the Runge-Kutta technique, and for this integration one has to start right behind the shock and integrate downstream in steps of small lengths delta x, which we basically talk about a grid spacing. So, if this is the shock location, then you essentially define points which are equidistant from each other at some small length delta x, and you keep integrating the governing equations along that line by incrementing the distance by delta x every time, and then you should be able to find out as a function of time how the flow properties are changing. So, you essentially cover the non-equilibrium regime, and where things stabilize and are not any longer changing as a function of x, you say that you have reached equilibrium conditions. The initial conditions that have to be imposed are obtained by assuming frozen flow across the shock, and as an example, when we consider hypersonic atmospheric flight, the free stream conditions are those for cool non-reacting air at the given altitude, while when a shock is formed inside a hypersonic wind tunnel, for example, the conditions upstream of the shock are calculated for stagnation properties and the area ratio of the nozzle. So, those details have to be input in order to obtain the free stream conditions. Now, let us come to non-equilibrium oblique shock wave flows. Here you find that we have introduced a curved compression corner and you have a straight oblique shock, which may be a little surprising to you, because we have already learnt that we need a sharp compression corner for a straight attached oblique shock to be formed. So, there must be something to do with the non-equilibrium flow over here. Note that the flow is crossing different portions of the oblique shock, and they would have different lengths to travel between the shock and the compression corner wall. So, the length that we are talking about is this. So, if you were to cross the shock at a location like this, then you would have a much larger distance to cross till you reach the wall, while if you cross it here, it will be a much shorter distance. And therefore, depending on this distance, things may be different. So, when you cross the different lengths, the shock normal velocity at the wall will be different in different portions of the shock, as long as the flow is still in non-equilibrium, and therefore, the normal component of the velocity which is seen just behind the shock is not the same as the normal component of velocity some distance downstream of the shock, because by then the flow velocity has reduced because of the increasing cooling that is being produced in the flow, and therefore, essentially the tilt of the velocity vector over here and that over here would not be identical. We will discuss this soon. If you were not tilting the surface and making it curved, but just leaving it as a straight compression corner, then a surprising result will be that there will be an attached oblique shock, but that oblique shock will no longer be straight. So, non-equilibrium flow over a sharp and straight compression corner produces this surprising result when you have a non-equilibrium flow. It is complementary to the surprise that we already saw over here, that across a curved compression corner there is a straight oblique shock. Now, let us go on to discuss a little bit further about why this may actually be happening. When we study the momentum conservation equation for the tangential velocity component to the shock, we find that the tangential component, the Vt, is preserved across the shock front. That is, Vt1 is Vt2 is equal to Vt3, and that basically means the velocity here, here or here are identical. It is invariant, and it is left as a homework problem for you to figure out why that happens. It seems to be completely unaffected by chemical reactions. However, the normal component of the velocity varies along the shock normal direction downstream of the shock, and this is characteristic of the non-equilibrium flow behind the shock wave. Now, why is it? We will try to explore that further. The oblique shock properties are basically determined by normal shock properties based on an upstream velocity perpendicular to the shock, which we call as V n1. So, the jump in normal velocity is basically the jump between V n1 and V n2. In the non-equilibrium flow behind a normal shock, density increases with distance behind the shock. Why is it? Because the flow is the molecules are dissociating, and that is an endothermic phenomena that we already talked about. The cooling of the gas is raising the density, while according to the continuity equation, the product of rho and the normal component of velocity remains constant, and therefore, V n must decrease with distance behind the shock wave to compensate for this density increase. Hence, V n decreases, and therefore, V n 1 is greater than V n 2 is greater than V n 3, while the tangential components remain conserved, which we already said. What is the consequence? The consequence is that the flow deflection angle theta A that you find right at the initiation of this compression corner is greater than the theta B that you find some distance downstream, is greater than is or rather this should be the other way around, that the theta A is smaller than theta B is smaller than theta C. It is by mistake put the other way around. So, what we are basically seeing is that there is increasing steepness of the compression corner that we see over here. The outcome is the streamlines in the non-equilibrium flow behind a straight oblique shock are curved and continually increase their deflection angle until equilibrium conditions are reached far downstream, and the root cause is that the V n 1 that is produced behind the shock continuously keeps decreasing because of the density rise. Therefore, in order to create a straight oblique shock front in a non-equilibrium flow, we have a compression corner that is shaped like a curved solid surface. This compression surface, after its initial discontinuous deflection of V 2 corresponding to frozen flow, must curve upwards until equilibrium conditions are obtained far downstream, where the deflection angle basically becomes theta C, and the curved non-uniform flow field in the non-equilibrium region behind a straight oblique shock front is an important difference from the familiar uniform flows that we have seen for calorically perfect and equilibrium oblique shock results. And for hypersonic non-equilibrium flow over a straight compression corner, the shock wave will be curved. The wave angle right at the corner corresponds to the frozen flow. Far downstream, the wave angle approaches the equilibrium flow value, and for a given deflection angle theta, the equilibrium shock wave angle is always less than the frozen shock wave angle. Again, if you were to look at the limits, then the frozen flow wave angle will be always larger than the equilibrium wave angle, and we have compared them over here. And to sum up the findings, the non-equilibrium flow behind a shock wave introduces a dimensional scale in such flows. We define a distance downstream of the shock required for the flow properties to reach 95% of their equilibrium values, which is usually defined as the relaxation distance. For any given flow, the relaxation distances are different for different flow or thermodynamic variables. For normal shock, these are much smaller compared to the oblique shocks, and this difference in non-equilibrium distance is because of the higher pressures and temperatures behind the normal shock wave, which would yield much higher reaction rates and therefore would produce lower relaxation distances. So, these are very important facts that you need to keep in mind. And we recapitulate the solution techniques for frozen, equilibrium and non-equilibrium flow. Solution of frozen flow is based on algebraic relations. Solution of equilibrium flow is involving a numerical solution where we couple all the equations and we incorporate the variation of gas properties as a function of temperature and pressure. Solution of non-equilibrium flow involves solution of differential equations, and that is how a length scale is introduced into the flow. Let us conclude by saying that in this lecture we discussed about distinction between frozen, equilibrium and non-equilibrium flows. We talked about characteristic time scales and length scales. Non-equilibrium flow past normal and oblique shock was discussed, and we found quite surprisingly that oblique shock shape over curved and straight walls were quite different compared to what we have seen for calorically perfect gases earlier. Thank you.